the distance required to stop a moving vehicle is the sum of the distances traveled during reaction time and braking time. The diagram below shows the theoretical stopping distances at various speeds. So, do you guys understand what it means by reaction time and braking time?
When the person hits the brake.
That would be braking time.
The reaction time would be when the car reacts to when the person hits the pedal.
You're driving on the highway. Don't judge. Okay? With your family. And all of a sudden you see a deer on the highway. The moment you see the deer, is your foot immediately on the brake?
Usually not.
No.
Ah.
Because there's a slight moment where you're like, ah, deer, what do I do? Right, brake. And then you put your foot on. I mean, you don't actually say it that slow in your head. But nobody is fast enough to instantly see a deer and instantly have their foot on the brake. So there's this delay between noticing the deer and putting the foot on the brake called reaction time. You are reacting to the situation, and that takes a little bit of time. Then you put your foot on the brake, that's the braking time. Get the idea? Now, the faster you're going, what's going to happen to your reaction time and your braking time? Is it going to increase or decrease the faster you go?
What? Like when you hit the brake?
So, I'm driving 5 kilometers an hour and I see a deer. How quickly do you think I can stop?
Not too quickly because there's that reaction time.
If I'm going 5 kilometers an hour, do you guys know how fast that is?
Oh.
You're barely crawling. Is it going to take me a long time to brake?
No.
No. So you'll have a relatively short reaction and braking time. If I'm going, 200 kilometers an hour and I see a deer,
Yeah, you.
am I going to have a longer braking time and reaction time? Definitely. So that's what this graph shows. Okay? So I'll just kind of walk you through exactly what it's saying. Notice here, this is your speed. These are different speeds that you could be going on the highway. Okay? This first number that you see is the distance you traveled while you were reacting to seeing your potential hazard. So for example, if I was going 90 kilometers an hour, it takes the average person 18.7 meters before they actually put their foot on the brake. So they're still driving, they see the deer, but they haven't done anything yet. They're still reacting. They're still processing what's happening. And they travel, on average, 18.7 meters during that time. By the time they finally realize, hey, I should put my foot on the brake, right? They put their foot on the brake, and then they travel another distance, in this case, 70.7 meters. Okay, so it takes them at 90 kilometers an hour, 18.7 meters to react, and then another 70.7 to actually stop. And then the total time it took is 4.92 seconds, so about 5 seconds, going 90 kilometers an hour. Does that make sense? Okay, and that's what this graph shows. And you can see, by the time I hit 130 kilometers an hour, my braking or my reaction distance is much longer, right? Because I'm going faster. And it takes a lot longer to stop as well, 135.6 meters. And it takes me just shy of 7 seconds to actually come to a full stop. Make sense? Okay. So A asks us just a really basic question. What factors might affect reaction time and braking distance? So what kind of things would take you longer to react? And what kind of things would take you longer to brake? Give me some ideas. There's no numbers involved here.
A moose?
Okay.
Or a collision with another car.
What you were about to hit, okay, so the obstacle could affect that, right? You might be more scared of a moose than you would be of a cat. Depending on who you are, you might accelerate if you saw a cat.
No!
I didn't say that.
So mean. It's
Okay, so the obstacle, what else can affect how long it takes you to react? Okay, your speed, sure. What else? Time of day. If it's 2 in the morning, you think you're going to be pretty awake and alert?
If you're drunk or not?
Yep. Day or night. If you're intoxicated, which I hope you were never while you're driving. Well, I hope you're never intoxicated, period, but especially while you're driving. Anything else? What about braking distance? Maybe condition of your car,
The weather.
the weather. Yeah, right?
If it's ice on the road, if you hit the brake, you might just.
You'll probably slide, increasing your braking distance. Lots of things can affect it. Good.
The horrible thing about hitting a moose is that if you hit a moose, you hit his legs and the fly.
Yeah. Yeah, it crushes you pretty quickly. Okay. So, if a vehicle is going 100 kilometers per hour, approximately what distance is traveled while the brakes are being applied?
1.8 meters.
That's while he's reacting. But what about while the brakes are being applied? So, let's look at 100 kilometers an hour right here. This is the reaction distance. And here's the braking distance. This distance in total is a little bit wrong, is how far they went in total. From the time they saw the thing to the time they actually came to a stop. So we want just this length here. How would we find that? How much bigger is this than 20.8? How would we figure that out?
Is 85.4, is that like all of it?
Yeah, in total.
Oh, then
Oh.
you just minus.
Yeah, you subtract them, right?
Oh.
So 85.4 minus 20.8. Yeah, I was a little mistaken there. I thought that's how far they went during their braking distance, but that's the total distance. It even says right there. Look at that. What is that?
64.6.
64.6 meters. So that's how long they had their foot on the brake for that distance. For this last one, we're going to convert 55 miles per hour into kilometers per hour, and then we're going to figure out the approximate stopping distance when a vehicle is going that fast. So we're going to have to use that chart in a second. So 55 miles per hour. Set this up for dimensional analysis for me. What's the first thing I do?
55 miles.
Miles.
Per hour.
Where does the hours go? Miles per
Oh.
hour.
Hours goes on the bottom.
Good. And what am I converting to? Miles per hour to
Kilometers.
kilometers per hour. So, what am I actually converting?
Is it miles per hour or is it
That's miles
meters
per hour. MPH is miles per hour. So I'm going from miles to kilometers. Can I do that?
Yeah.
Yeah. What? How many miles in a kilometer? Or kilometers in a mile? Doesn't matter.
1.609
09
kilometers.
kilometers is a mile.
Yeah.
Okay. So set up the fraction. What goes where?
1 mile goes on the bottom,
Good.
and then kilometers goes on top. And
Good.
then they would cross each other out.
Okay.
So then you're just dividing.
Now hold on. I want to go miles per hour to kilometers per hour. Do I need to do anything with this hour?
Yeah.
No.
Oh.
I want kilometers over hour. That's what this will give me, so I'm just going to leave it.
Oh.
So let's multiply. 55 times 1.609, that's essentially all you need to do. How much is
Oh,
that?
so we just 88.495.
88.495
Yeah.
kilometers per hour.
Wait, what? I got.
You're multiplying them.
Oh. Divide.
We multiplied. You just you entered in the wrong thing here. It's supposed to be 1.609. You put 0.069.
Oh.
Okay, so we want to know the stopping distance. Look at the chart up here. What's the thing that's closest to 88.495 kilometers per hour? What's the closest thing? What's the closest speed that we have on this chart? 90, right? So we'll just use 90 to approximate the braking distance. Is that what they want, braking distance? Stopping distance, yeah. Okay, so just like we did last time, how far did they go in total? Going at 90 kilometers per hour?
70.7.
They go 70.7, and then they react for how long? 18.7, so we just subtract them to find out. So 70.7 minus 18.7 is how much?
52.
52
Yeah.
meters. So that's how long it takes them to stop approximately. Good? All right. Awesome.